IBM defines computer vision as an AI field that uses machine learning and neural networks to teach computers to derive meaningful information from digital images and videos. Consider this analogy. If AI functions as the brain, computer vision serves as the eyes. As humans, we effortlessly understand our surrounding environment with all its nuances. We can distinguish moving objects, changing shapes, and different colors. Sometimes we can notice the slightest differences and the most subtle details. The study of computer vision is a monumental effort to develop sophisticated AI models that allow computers to comprehend real-world information. To do that, computers consume input through images and videos. Images are simpler because they capture a single moment statically. Conversely, videos are more complex, appearing as continuous sequences of images, for example, 30 frames per second, that require processing. The computer must analyze each frame and understand its context and continuity. There are 4 main families of computer vision models. First, we have convolutional neural networks. CNNs are foundational for computer vision because they are great when working with high-dimensional data. In the early days, AI researchers used other types of neural networks for computer vision problems, but they struggled with high-dimensional data images due to the immense number of parameters required. In contrast, CNNs are great at capturing spatial hierarchies in images. But what does this term mean in plain language? It means that CNNs are great at organizing the elements in an image based on their importance and depth. Imagine looking at a picture where some things seem closer to you and others farther away. The foreground is up close. The middle ground is between, and the background is distant. Larger objects often appear closer and more significant. Overlapping items make those in front look nearer, and centered or top-positioned elements typically attract more attention, enhancing their importance. CNNs are effective at processing information due to their layered structure. This enables the network to learn basic features, like object edges in initial layers, and progressively capture complex, high-level features, such as shapes and objects, in deeper layers. Next, we'll focus on transformers, a key topic in our upcoming discussions on generative AI. For now, we can just say that, in some cases, AI researchers apply transformer architecture to images for the purposes of computer vision. Third, generative adversarial networks, GANs, primarily create lifelike images. Lastly, specialized networks, like UNet, excel in medical image segmentation, while EfficientNet optimizes performance by efficiently scaling neural network dimensions and utilizing computational resources. Computer vision has a ton of exciting real-world applications. Self-driving cars, medical imaging, security, surveillance, and other areas we previously discussed show great promise in robotics. It's important to remember that computer vision does not need to be part of robotics to be an incredibly useful product. For example, consider face recognition software. It's just a model built into a software product without a robotic body. Some of the most exciting advancements in computer vision are currently in virtual reality, revolutionizing such industries as education, entertainment, and long-distance communication. In our next lesson, we'll discuss traditional ML methods. Thanks for watching.